Good afternoon. How is everyone?
Very well, thanks. Afternoon, Charles.
Afternoon.
Yeah. How have you been getting on with Lambda calculus recently?
As soon as I think I've understood it, it decides to elude me like herding cats. So,
Okay. Did anyone bring anything they want to show off? Anything they've been doing recently for the module? Anyone totally stuck with anything?
I'm not sure I want to show it off because it's not quite finished or anything, but I'm trying to implement it in C#, so do it more object oriented.
Okay. Do you have anything to show? Do you want to share your screen?
I could if you want.
Yeah,
I've managed to get one which does very basic like substitutions. Is this one? Okay, hang on. It was one of those things where I was trying to do it, and then like for a couple of hours, and then at one point it just sort of clicked, and I was like, "Oh yeah, I can do it like this." Okay, let's see. Share screen. So it's using like the Pi Lambda is a lot of influence for it, but it's basically instead of doing it in the Pi Lambda has, it will just I'm not sure how it does it, but it has the whole define expression or define variable and things like that. So in what I'm trying to do, it has this the back is no form, and I was sort of just trying to go off that, and I understood that everything can be an expression, and then expressions can be made up of the names, the functions, and applications, which in themselves could be expressions. So I was trying to see if there's a way that I can make it so that if it's classed as an expression, then you can just have it so it's object oriented in a way that an expression can go into an application, which can go into more and things like that. Okay. Which I'm not sure if that's exactly like the tree structure that you were mentioning before.
Yeah, if you have a class of expressions and then subclasses of that for functions and applications and so on.
Yeah.
Yeah, you'd absolutely end up with a tree being formed out of that.
Okay.
Each of those expressions is going to contain a bunch of other expressions. Yeah.
Yes. Yeah. That's what I've sort of come up with here. So it has the whole thing where in an expression, it initializes. It can either be a name function or application, and then it checks if what it is by using these functions is application or is name, which is what I think is similar to what it uses in the Pi Lambda one. Apart from it just uses the built-in Python function of is instance. So I sort of converted that into this C# style thing of doing it myself. Then I have one which is like is normal form as well, which is also in Pi Lambda, but it just instead it uses this is normal form in each class. So the expressions can be done in each one of these. So it has a variable, or a variable of name, function, application, and then inside each of those it has in name it just has a string of name in application, and that's just a very simple one where you can set the name and then get the name or check if it's normal form, and of course for name it always is normal form. Then in application, that's when it started to get a bit complicated for me, because I wasn't sure exactly how to follow it. But then in the application one, you can have another expression, which is the first and the second one, and those are similar to Lambda as well, where you can just split those off and go down those sort of tree branches to the sort of substitutions and things like that. And that's very simple as well, where you can initialize it with an expression. I think I can get rid of this one now, actually, because it has no references, and it was something else I was trying to do. But you can initialize it with the two expressions, so the first one and the second one, and that just has, again, just to get where you can get. Oh, I think I can get rid of this as well, actually. But yeah, there's like the set stuff. And then with the function as well, it just has a name and then expressions. I think as well, again, this one, you don't really need this one anymore, but yeah, you can set an expression basically, and it keeps going down there. And then of course it just has, to do it, you just put it in as a string, because that was another thing that I was sort of struggling with as well, was trying to figure out how to get an input from it and then turn it into this tree structure. So I sort of use a similar thing from the PyLambda as well, where it has a parser. But I think that I was struggling as well, because there's a PyLambda one uses this PLY. Is that what it uses to parse?
Yeah, so PLY stands for Python, Lex, and Yak. So it's a Python wrapper around two very standard parser libraries called Lex and Yak, otherwise known as Flex and Bison in their open source versions.
Right.
So those are the things that are often written to write real language compilers. They're a little bit overkill for this. This one can be done much more easily. So, for example, I just put up another Lambda interpreter on Blackboard. I put up an example of a Lambda interpreter written in the language ML that we talked about last week, which is very simple indeed. It's really just a couple of screens of code, and it does the whole thing, including defining the full set of combinators for the user to use. So ML is designed for this kind of work. It stands for meta language. It's a language for making other languages. So it makes it very easy. If any of you guys are doing functional programming, is anyone learning Haskell or anything at the minute?
Yeah, of course.
Yeah. If you're learning Haskell, you should just about be able to read ML. They look and behave very similarly at this level of things. In fact, you might not even notice the difference. You might almost literally be able to take the ML code and paste it into Haskell and make a few very superficial tweaks to run the thing. Yeah, very recursive functional languages are always good for language design. So, okay, this C# one then. What does it do so far? Can you do anything yet, or are we not at the stage?
Yeah, so I can do like the very basic stuff. I've only implemented the beta reduction as well, so it can't do any of the alpha conversions and things like that.
Yeah.
But it's like before I do that, I'll like pause it at here, or here, so we can see, like, I'll show you like how the structure of it works, because that's how I sort of got my head around it. So if I just do the basic one of X, Y, we'll go through, and on the actual screen here, it does the beta reduction to get you just Y. But in the actual variable of it, you can see that it has this expression so like just the getter is the string version of it, but then inside the actual, I don't know how easy it is to see because how small it is, but in the actual variable, it has an expression which is then split into an application of first and second of two expressions. And of course, the second one is just the name of Y, which is the second half of the statement or term. And then the first one is the function. And then even though it's a simple one, that's why I was like starting to get a bit lost with it sometimes. But then even in that one, the first is the function. So inside that function is another expression and another name. The name is X and the expression is X as well. And then it goes through that, and then it will just convert it through there. So you can do quite a few, which I'll keep going.
So you can parse that expression, you've got it into a tree, you can deeply reduce it, yeah?
Yeah.
So
it's just the very basic ones as well.
Done apart from alpha conversion, yeah.
Yeah, and there's some things like, because I need to add a couple more, I think a couple more conditions, which will say that if it's, because I'm splitting it by the brackets at the moment, so it's just getting each one. So you can do one of these, fine, and it will do, okay, so X can go into, this can go into X, and it will just give you that one, and then lambda Z can go into Y, and it will give you that one.
Yeah.
But if you look at this one again, it will have a similar thing where it has an application with expressions inside it, and inside that is another application which has more expressions, and then so that's sort of how it works, where it just goes through this tree structure of trying to find the first and second expressions, and then match that expression by the name in the like the lambda of the name of the lambda, and then replace the things in the expression of that. So I think it's very similar to just how the pi lambda works, but implemented in C# instead.
Oh, very nice. That's a beautiful thing to see.
Thanks.
Thanks for sharing. Yeah. And
No
do you get the feeling that alpha conversion is kind of fiddly at this point?
Yeah, I'm not 100% sure how I'm going to properly implement it, and I mean, I'll be able to have all of the expressions and everything like that separately, but then I think it's just going to be a way of trying to figure out how to. I think it's just I need to implement how to do the free variables and bound variables first, and then once I get that sort of all sorted, then I can definitely get a little bit more of a handle on how I'm going to figure that one out.
So yeah, most of these interpreters they'll build that stuff up. You know, you'll have a function to check if x is free or bound in something. Maybe a function just to check if x occurs in something at all, and then a function for doing substitution once you've decided it's going to happen, and then alpha conversion is going to call all of those in the right order to do its thing. So you always think of breaking up the tasks into the simplest pieces that you can. Nice example of that in the ML version I just posted. It's a very clear function for finding instances of x, checking if they're free or bound, doing substitution, doing alpha conversion. Okay, good. Really beautiful to see. A couple of people are still asking me, do you actually need to do this? Do you actually need to write your own Lambda interpreter? I would very strongly recommend that you at least try, because it's an amazing learning experience, and it's a very classic learning experience. You know, to pass the assessment, you don't actually need to, because it's been worded very carefully. So it only says describe the design of a Lambda interpreter. So the words don't say that you have to describe your interpreter. You could describe the design of any interpreter. Although if you're writing about your own, you will really know what you're talking about and be able to give a very good answer, and B, you will just look very impressive to an examiner who sees that you've actually got one. So, you know, when I was a student, we didn't do a whole lot of implementation in these more theoretical courses, and I missed that for a long time. We spent a lot of time just studying the theory, and it's, unless you at least have a go at it, it's quite hard to see how the symbols on the mathematical pages and slides actually map into code, or it can feel a bit intimidating. So, you know, it's actually very simple. You know, whenever you see a grammar, you see the expressions and the terms and the variables. You know, they're literally just classes and objects in your favorite language. There's always going to be a class expression, class application, class function. You're going to put stuff in there to represent them. Maybe you make a nice toString function that makes it print out something that looks a bit like what's on the lecture slide. But the idea here is to overcome that fear of code when looking at theory. You know, it's actually not that hard just to take the symbols from the side and turn them into a bit of code. And that's pretty much all that happens in real life. You know, you'll see much bigger versions of this in actual language design or in AI or theorem proving, and that's all they do as well. You know, they represent the expressions, they process them, just like any other kind of programming. Okay, anyone else want to give us an update on anything, or any questions before we start? No? Okay, so if not, I wanted to make time at the end just to get people in the workshops, because it's nearly assessment writing time for the Lambda part. So we'll try and make plenty of room at the end for discussions, and I'll go straight into talking today. So in the last couple of weeks, then we have looked at the Lambda calculus as the original definition and model of computation. And I hope you've all had at least a quick look over Church's original paper. Again, don't expect anyone to actually understand it. I don't understand a lot of it, but you can at least get a flavour of what Church was doing. You can see where Church's thesis shows up. You can see where the Church-Russell theorem shows up. The definitions of Church numerals, and the definition of computation in Church's thesis is there. So everyone should at least have a look over it and be aware that it exists. So, also in 1936, other people were thinking about this stuff. There was a whole community of logicians, or proto-computer scientists, who at the time were called logicians, all thinking about similar questions. There were lots of similar ideas floating around. Everyone was going to the same conferences, reading each other's work. And one of those people was Alan Turing here in the UK. And he came up with a different model of computation a short time after Church came up with his, which it turns out is pretty much equivalent to Church's model. So Turing's machine, which is now called the Turing machine, I think Turing just called it the machine, it has been very influential historically in our subject because it looks rather more like a practical computing device than Lambda calculus does. So to build a physical machine that executes Lambda calculus is not completely obvious how you're going to do it. Okay, I think you guys all seem quite happy building one out of another computer, out of another programming language. But if you didn't already have a computer, it's not straightforward what you'd actually build out of physical bits of metal or plastic to implement a Lambda calculus interpreter directly. So Turing was coming from the other way. Turing was looking at the machines that already existed out there. Things like this. This is the Wheatstone telegraph from 1867. It's an automated telegraph machine, so sending and receiving Morse code. And what you see here is a long piece of paper tape with holes punched in it representing zeros and ones, and you can see there is a head which is reading or writing to one particular location on the tape at a time. And there was a whole family of machines like this in very common use by 1936. So back in computer architecture, we looked at the Babbage engines. The Babbage design is a full-on modern CPU architecture made out of this kind of paper card mechanical technology. So Turing would have been aware of that. He would have also been aware of the IBM computing machines that were already being sold all around the world, including being used in Bletchley Park before Turing even showed up there. And some of these machines were in common use in the UK Post Office. They're doing sorting, all kinds of calculations, tabulations. So the government census, we're just doing the census now. Right? Everyone got their census 2021 form, and they're processing those censuses. Processing the data from the census was a major driver of these machines, because particularly in America there was a official statutory rule that statistics had to be computed from the census data, and it was just impossible to do it manually. So the government really had to invest in these machines. And they were doing that a long time before Turing was even born. So, Turing's take on all of this wasn't to invent another one of these machines. Those machines already existed. Turing was interested in the same logical problems that everyone else was interested in. Okay, the spirit of the time had come from Hilbert's program. And remember, Hilbert has this dream about how do we formalize all of mathematics and turn it into logic, and then ideally have it prove itself correct, and then you have the logic, the one true mathematical system. And Gödel had just come along in 1931 and blown all of that up. And so at this point, people are picking up the pieces from that, and they're trying to understand what the properties of logic actually are. What are the limits of logic in this new postmodern, post-Gödel world where logic and mathematics actually aren't perfect anymore. And there's this element of subjectivity in choosing which logic you want to use. So, Turing was interested in that primarily, in being part of that community, and in particular, he was interested in this problem of are there problems which have no algorithm? Are there uncomputable problems? Okay, that's the same problem that Church had just solved when we saw Church's version of the halting problem in the Lambda calculus. So Turing wasn't aware of that at the time, possibly because Cambridge still has a reputation of not invented here syndrome. Church was over in America. Cambridge often does its own thing, and Turing was doing his own thing, and he just hadn't read the stuff that Church was doing at that point. And he could have saved himself a lot of time if he had gone out and read what Church was doing. He later read Church's stuff and went over to become his PhD student to actually find out about it. But Turing was doing this independently at the time, and so his idea was to go out and look at this class of mechanical computing machines that were out there in the real world and use them as a model of computation to go and try and solve this decidability problem. Are there problems that are uncomputable? So where Church had come up with this very abstract Lambda calculus tool to help him do that, Turing is going to use this much more mechanical inspired model. And the Turing machine then is a very simplified version of all those other machines. You can imagine taking the Babbage engine, and maybe this is what Turing actually did. You could take the Babbage engine and try and strip it down. The Babbage designs are very, very complicated. They're working in decimal for a start. They have this huge instruction set of many different arithmetical operations. They have quite complex punch cards that are two-dimensional, with each row containing a whole bunch of instructions. So you can rewind and fast forward the punch card, but you can also choose which column along the row you're interested in. So, all of that complexity is probably very useful for a practical computing device. But if you're doing theory, as Church was doing, you want your model to be as simple as possible because that makes your life easier as a theorist. If you're going to have to prove that the machine always does something or never does something, you've often got to consider all the different cases of what the machine might be doing. And if you've got 20 different instructions, it's going to be very hard work to prove anything because you've got to prove it every time for each of the 20 instructions. So what you want is something like the Lambda calculus or the Turing machine, which simplifies the action of the machine to its bare minimum, and then you don't have as much to do. Right? If the machine only does 3 things, then you've only got to prove 3 parts in all of your mathematics. So this thing was never intended to be a practical computing device. Okay, it is intended to be a mathematical abstraction of those punch tape devices that already existed, and it isn't practical. If you ever tried to build this, it would be ridiculously slow and would do a lot of very silly things that are not required in practical computation at all. But if you want to do theory on it, as with Lambda calculus, it's a nice, simple abstraction of what the real machines actually do. So, like this whetstone telegraph device, Turing's model simplifies the whole idea of memory down into a single paper tape. Okay, and each point on the tape contains a binary symbol, a 1 or a 0. That could be represented as a punch in the tape? Actually, not very easily, because the machine's required to update the symbols by writing ones and zeros. So it's actually quite hard to fill in a hole on a tape. Yeah, you'd have to put an extra piece of paper on it and some glue or something. Nowadays we have magnetic tape, so the cells could represent zeros and ones by the north or south pole of a magnet. That's what you get on an audio tape or in a magnetic hard disk. But Turing just doesn't care, because this is a mathematical abstraction. Really, when we talk about the tape, we just mean an infinitely long array that can contain zeros or ones. And the point is, you can access one cell of that array at any one time. So again, he's using this nice metaphor of the computing machines. You can think of it as a paper tape that is moved left and right. Your head is staying in place, and so your head can read and write to any one square at a time. And if you want to read and write somewhere else, you're going to have to move the tape. So importantly, this is not a RAM. It's actually quite complicated to program, because it's not a RAM. You can't go directly to location 57 and write in it. You have to go left, 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 left 57 times to actually get there before you can read and write. But again, Turing doesn't care about the speed of it, because that's not the point. The point is to try and answer this question of whether there are uncomputable problems out there. So roughly, a Turing machine then has two components. One is the program and one is the memory. And the memory is this unlimited tape. Well, in abstract terms, it's an unlimited array. And it all starts off with zeros on it. So if you run any realistic program on it, there will always be a finite number of symbols written on the tape, because any program that actually ends, halts, and gives a result has a finite number of steps, and it therefore has a finite number of locations on the tape that it is able to visit. So sometimes you hear this described as an infinitely long tape, and that sounds rather too scary. The point is that the tape is unlimited. You're not actually covering an infinitely long tape with stuff, usually. Rather, you just have as much tape as you need to do your calculation. If you run out of tape, then it asks for a bit more, and you can go and glue some onto the end of it. Now, this is similar to modern computer games like Minecraft. Okay, Minecraft is advertised as having an infinitely large world, so you can just keep going and going, but you never see infinity in it. You'll only ever see a finite amount of world in Minecraft, unless you're immortal and you play the game for an infinite amount of time. So Minecraft is actually a very tractable game. It's advertised as having an infinite world. It actually just has an unlimited world. It means you can keep going and asking for a bit more whenever you need it.
I think with it actually, there is a world limit, but it's like 32 million blocks or something. It's utterly ridiculous, and pretty much no one's going to go there. And there are people who have actually decided, like, you know what, we're going to go there and see what happens, and it just glitches. It just breaks. The world generation goes kaput.
I was promised an infinite world when I bought the Bedrock edition. I shall be demanding a refund if it has an end. Okay, so look, that's all that is meant by this unlimited tape. Yeah, it's not a scary infinity. It's just the ability to add more tape as it is needed. Yeah, and the other component then is the program. And the program is to be represented by a finite state machine. Have you seen finite state machines before anywhere? No?
Everywhere. They show up literally everywhere.
Yeah, okay, good. Has everyone else seen a finite state machine before?
Yes, we did. a little game of life thing in first or second year, I think.
Okay, good. Yeah, so we often use them in robotics, right? You know, the robot is either in a state of walking forwards, and you know, you say, have you hit something? If you haven't hit something, you can carry on walking forwards. You know, when you've hit something, you might go into a start turning state. You know, turn left, and maybe you do that for a while, and then you go into your next state. Maybe your next state is walking forwards again, and now you're walking in a different direction. Yeah. And from Matthew.
Hiya. Is the concept of a finite state machine at this point in history developed as like a field, as like a concept?
Oh, that's a good question. I think it probably is, but I couldn't cite anything to prove it.
Right.
I think there's a lot of people in this community using them for different things. Probably not called a FSM, probably with a different name.
Okay.
Okay. Yeah. Good.
Oh, well,
good
we'll have a look at the paper and see what he calls it. I don't know.
Yeah. Okay. Good. Okay, so when we talk about the Turing machine, it's not really correct because the Turing machines are a family of machines, and each machine has a different finite state machine, and that is the program. Yeah, so you're going to create a Turing machine for your program, and the particular FSM in it is the embodiment of your program. There we go. One Turing machine per possible program. So the state transitions in this finite state machine, you know, in my robot, they're driven by the sensors on the robot. Am I looking at a wall? If so, move to another state. In Turing machines, they're driven by what is on the tape. So the only sensor you have is look at the tape and you can say, is it a 1 or is it a 0? So here, S0 is the symbol for 0, S1 is the symbol for 1. Why not just write 0 and 1? I was wondering. Yeah, you could just write 0 and 1. So, you know, here we have 3 possible states that the machine can be in, called Q1, Q2, and Q3. So Q is the traditional symbol for state in all kinds of engineering and mathematics. And you'll find it in control engineering and stuff from before this time. And what we're saying here, in this notation, the symbol on the left is the input. What are you currently looking at on the tape? So if you're in state number 1 and you're looking at a 0 on the tape, what you're going to do is you're going to write a 1 on the tape, and you're going to follow the arrow, and you end up still in state 1. Okay? Now at this point, the symbol on the tape isn't a 0 anymore. You now have a 1 on the tape. So at this point, you've now got this one to follow. So you're going to follow this transition because you were in state 1 and you're seeing symbol 1. And as you do this transition, you're going to do this action. So this action was writing a symbol. This action is go left. Okay. Depending how you set this up, this could mean move the tape head left, or it could mean move the tape left. It doesn't matter which way around you think of it. Let's imagine it as like an audio tape, and say you're moving the tape left, like a fast forward or a rewind. Okay, so now you've moved into this state. Now you are in state 2, and you're going to say, what am I looking at on the tape? If I've got a 0, then I'm going to do this. I'm going to output a 1. I'm going to write a 1 on the tape, and I'm going to go to this state, which is still state 2. Yeah? And at this point, because I've just written a 1, I now don't have a 0 anymore. So now I'm going to follow this transition because I'm looking at a 1. And again, I'm going to move the tape left, and I'm going to go to the next state. I'm going to go into state Q3. If I'm looking at a 0, I'll follow this transition. That means I'm going to write a 1, and I'm going to end up in Q3. If I'm not looking at a 0, This is interesting because there's nothing for me to do. There are no arrows coming out of here that say what to do if I'm looking at a 1. So if I don't have any arrows, then I stop. Okay, that's called halting the machine. We run out of things to do, and that's the end of the calculation. And whatever is left on the tape at this point is the output. So actually, what does this machine do? If you were to run this on a tape that was initialized with all zeros, so in general, you can start with any input on your tape as long as it's finite. The default is everything 0, but if you want to write an input on it with a finite amount of stuff, you can also do that. So what would actually happen here if you've got a tape full of zeros and you start off with your tape head here? So what's going to happen first? You always start off in state 1 as well.
Let's see. Well, the program says if there's a 0, move to state 1. So we're going to go right.
Yeah, if there's a 0, we're on this transition. Yeah. Yeah. So we're gonna go to state 1, which we're already in. And what are we doing here?
Then we start in state 0.
We've started in state 1. The states are numbered from 1 to 3 in this case. There's Q1.
Oh,
Q2,
okay, yeah. Yeah. So what does S stand for here?
So S
That's the
is
symbol. That's S
symbol.
for symbol, not for.
Yeah. Q is for
Okay.
state. Yeah.
Yeah, because otherwise it would be outside of the circle that the finite state machine is in. Because yeah, obviously.
Okay.
So it's saying if we see a symbol 0, is that saying to write a state 1? A symbol
Okay,
1
so
rather?
Yeah, so we've seen symbol 0. Yeah, we're going to write symbol 1. So at this point, we're going to delete that, and we're going to write a 1 in that square on the tape. Okay? So we've got zeros all over the tape. Okay? Yeah, so the head's here. We've seen that 0. We're going to write a 1, and we've ended up still in state 1. Yeah? So what happens next?
Well, we're going to do another read because we haven't moved anywhere along the tape.
Yeah.
So we're currently in
what's
state
the
1 still because the diagram's saying we're going back on itself. So we're going to read. We see that we have a symbol 1 on our current place in the tape. So we're going to move to state 2.
Yeah, and what are we going to do as we move to state 2? What's this?
I assume L is shift.
Yeah.
Shift left.
Actually, on this slide, I've written it as shift the active location left or right rather than type. So let's follow what I've written on the slide. Yeah, okay. That means we're going to shift the active location 1 step to the left. Yeah.
Yep.
Which is equivalent to pulling the tape a notch to the right, depending on your point of view. Okay, good. So now we're here, and we're in this state. So what happens now?
We're in the current state. We can either, well, we only have 2 symbols or states, so they both start with an S. This is really screwing me.
Yeah. Okay, so we're looking at a 0.
Yeah. So we're currently looking at a 0. So we read off a 0. That means that we're going to write a symbol 1.
Yeah.
And so it's the same. It's not the same state, but the state has the same, I want to say, semantics.
Yeah, it's done the same kind of thing that we did before. Yeah. So, and what state have we ended up in?
We are still in state 2.
We're still in state 2. Good. Okay. And what happens next? What are we looking at now?
We're reading a symbol 1, so we're going to shift left and move to state 3.
Okay. So now we're going to shift. Yeah, let's say we're shifting the head left. Now the head is here, and we're in state 3. Good. And what happens now? What are we looking at?
Then we're going to repeat our read and write of symbol 0 to symbol 1.
Yeah.
But now, so after we complete that transition between states, we've ended up at state 3, but
Mhm.
we can't read off a symbol 0, so the program halts.
Yep, good. And so that's the output. The output tape now has these 3 ones written on the tape in the row. Okay, good, good.
Oh, that's considered technically output there, is it? That's interesting. Because I would have said it's more like side effect like behavior.
The output is the final state of the tape. Okay.
Yeah,
They finished the
that's interesting. It feels less neatly bound up in the same way that lambda calculus is.
Yeah, so you can feel this is going to get dirty, right? You're going to have to clean up a load of stuff on the tape if you want the output to look nice.
Yeah, separating. I think this has to do with because of how separate the program and the data that it's acting on are. You have to make changes to a thing, and then you have to move along it instead of being able to quite expressively say, well, you need basically function-like syntax. So you have no purity. It feels like.
Yeah. So actually, what kind of architecture is this from computer architecture, where the program and the data are completely separate?
Von Neumann?
No, the other one.
No. Oh no.
Harvard architecture. Harvard architecture.
Von Neumann is literally the opposite. I thought. Yeah, no, actually, this was a question I wanted to ask. Is reading the data in order to make changes to the program during the execution of a model, because if we already have the entire power of a finite state machine just in the program, then the equivalence of program and data while it's reading along the tape shouldn't. It's obviously a lot more expressional to do in the lambda calculus, but that's the way you wouldn't be able to do it in this.
Okay, so look, what would happen if we ran the same program with a different input? Let's say we started the tape in this configuration. And I don't actually know what this is going to do. Let's say we start in this configuration with the head here. Okay.
I think that no matter what the input is, it's always going to have 3 ones from the current position and to the next 2 positions.
Okay, so let's try that out then. So we're in state 1, doing it orange this time. This time we can see a 1, can't we? So we've seen this 1. That means we're just going to go left. So now we are here. Yeah? All right, now we're in state 2. We can see a 1. So we're going to go here. Yeah? Now we're in state 3 and we can see a 0. So this time we're going to go this way. And that means we're going to rewrite that as a 1. And now we're in state 3, we're looking at a 1, so we're going to halt. Yeah, so this appears to be, this is just a totally random Turing machine. Right? I didn't actually know what it was going to do until we worked it out. This appears to be a machine then that makes you have 3 ones. It's fixing the tape into the state of having 3 ones. Or at least the state of having 3 ones around the starting points. Because you might have started your tape in some crazy state with, we don't really need the...
No, I think it just, unless there's ones outside of that range, it's basically like a logical OR with 1 on from the position that it's given plus 3 or minus 3, depending on which way you want to have the
so it only cares about these 3 numbers, right? That's all it ever looks at, and it ensures that they're all 1s, and anything else on the tape is just left as it is. Yeah? Okay, good. So let's formalize this a little more. Because the Turing machine is such a big thing, there have evolved many different ways of notating them, right? So this is the notation we just saw, drawing out a finite state machine as a picture. So you can display that exact same program. Remember, this is the program for the Turing machine. you can display the same thing in a couple of other ways. This way is maybe what you want to use if you're going to simulate a Turing machine. If you want to write a C natural program to simulate Turing machines, which would be a great exercise, though not as accessible as the Lambda calculus one. This is pretty much how you want to notate your program. Here you've just got a 2D matrix, and this is the present state you're in, Q1, Q2, or Q3, corresponding to the three states here. And this is what symbol are you looking at. So this is a nice representation, because when you run it in a simulation, this is what you actually want to look up. You're going to say, I'm currently in state 1. What symbol am I looking at? Oh, it's a 0. And then you can read out, here's what I'm going to do. And what I'm going to do is some combination of writing symbols and or moving. So here we're doing a left and going to state 2. Here we're writing the symbol and going to state 1. Okay, you will also see this notation, and this notation is very useful in the theory, in the meta logic of Turing machines. We will see that later. In this notation, you describe the machine as a set of quadruples. So it's exactly the same information as in the other two, but here it's notated as the starting state, the symbol you're reading, the action you're going to take, and the state where you're going. Okay? So can anyone guess why this is most useful in the meta logic already? No? It's the one that makes the whole thing look like a big number, right? We're going to do things like mapping programs onto numbers. And in this case, all you've got is just a bunch of symbols all written in a massive string. And it's easier to deal with that than it is to deal with complicated things like arrays or pictures. So if anyone's looked at Gödel numbering, we're going to be able to do Gödel numbering very easily on this and consider this simply as a single big integer number. You could imagine writing this out in ASCII, and a file of ASCII can be represented as a single big number. In fact, that's what it is. It's a single big number. And so you can very easily go there because there isn't any extra symbolism. Here we're relying on the 2D structure of the paper to make this little matrix, or the 2D structure of the paper to draw this little figure. But this is just a string of symbols that is much easier to manipulate. So let's use QI for the states. The actions then can be left and right, and or writing a symbol. If no action is given, then you halt, and the output is whatever's on the tape. So we always start in state Q1, and we always start at tape location 0. The tape can start with any finite number of ones on it. That's the input to your program, but not an infinite number of ones. It's got to be a set of ones that you can actually write on the thing. And the rest of the tape, think of it as being initialized to 0. So for example, here's a line in this notation. This means if you're in state 2 and you are reading symbol 0, then do an action, which in this case is write symbol 1, and go to state 3. Okay? If you would like to look at this as logic, so one thing I'm trying to do in this module is put everything into logical form so that we can see the similarities. Here is a way of writing that same process as a sequence. So let's represent the state of the machine as a triple. So the state of the machine is what state am I in? That's my input state. what position am I in on the tape? That's the location of the head on the tape. And then what is the state of the whole tape? What are the numbers written on the tape? And this triple completely describes the state of the Turing machine. So Q is a state, and remember there are a finite number of states, so it goes from 1 to n, where n is a upper limit. Remember P is an integer. It can be either positive or negative, and it's unlimited because you can go in either direction. And let's use this notation. Let's think of the tape as if it's an array. So we'll say the pth location on tape T is a Boolean. It's either 0 or 1. Okay, so in my sequence here then, I've said this is an input condition. If the machine is in this particular state, now we do some pattern matching. We say, is the tape at the current position showing a particular symbol? So this is now going to describe the transition. So we're saying we're definitely in, the system as a whole is in this state. We're in this FSM state, Q in. We're matching a symbol. And then this is the program. There's a few different ways of notating this. What I've done here is written a single rule that applies to every Turing machine, because I want to show that Turing machines only ever do one thing. So look, if you're in this state, if you're looking at this symbol, and if there is a rule that looks like this in your finite state machine, so we're assuming now that the programmer has just given you a list of these FSM instructions. If all of those things are true, then you may go to the next state. And the next state is Q out, which has been pattern matched from over here. Your position can either move left or right. So in general, you've taken your input position and you've added either 0 or 1 or -1 to it. That represents shifting the tape or the head left and right. And the other thing you've done, this notation means the tape has changed. We're going to substitute the symbol at location P in for the symbol S out. Okay, so I'm actually using square brackets doing two different things. This square bracket means substitution. It means take the tape, but change it in a way that makes the substitution. And the substitution is using it to say make the P in location equal output symbol. So here I'm going to use array notation.
Yeah, I was a little bit confused by that notation. Would it be just as a would it be easier to use something different from equality to binding when using the equal sign?
Yeah, maybe you want something like a little colon before the, yeah. Well, how did we do this in, somewhere we used a notation with a backslash, I think, with TPIN backslash S out. I think we've done that in a couple of places, in Lambda calculus. Yeah.
So substitution. So you're substituting
we're substituting this symbol for
right?
this. Yeah. Which other way around it is? I can never remember which way the Lambda calculus. Pick one and define it in your sides and get on with it. Yeah. Okay. So formally, you also need an axiom to get the machine started. And here's your axiom. So the axiom has no preconditions. There's nothing above the line. And this says you always start in state 1, you always start at location 0, and it says you can start the tape in whatever configuration you like. So someone's given you a particular configuration of the tape called tau, and that's how you're going to start the tape. Now, in this notation, what I hope you can see is that there is only ever going to be one thing you can do. You're going to start with the axiom, because that's all you have available, and that proves that you're in this state. Yeah. Now you're in this state, you can apply this rule, and as long as you can convince yourself that the FSM is deterministic, which it is, because it's defined as such. I just put it in the definition. There's only one rule you can ever apply. So the Turing machine is completely deterministic. It goes from one state to the next. And you don't have to choose what rule to apply, because there's only ever one. Now this is different from the lambda calculus, because in lambda calculus, you have to choose your strategy. You say, which beta reduction do I actually want to do? Or do I want to do a beta reduction or an alpha conversion? So for lambda calculus, our life was a bit harder, you know, and you see this when you write your implementation. You see you have to make a choice. So you're doing something that looks like call by name or call by value. But remember, for lambda calculus, we then saw the theorem. We didn't prove it, but we saw the Church-Rosser theorem. And that is a piece of meta logic that proves that it doesn't actually matter what order you run the rules in, because you always end up with the same thing for lambda calculus. You know, when you look at other forms of logic, like the kinds of logic we get in AI, where you're actually trying to make an argument, you can get very lost indeed, because at any point in time there are lots of different rules you could apply. You know, we saw this in the MIU system. You know, you guys, some of you had fun for many hours trying to choose the right sequences of rules to apply, which ends up looking like a program. It is a program. But with a Turing machine, it's much simpler, because there's only ever one thing it does, and it's completely deterministic. So we don't have to go and prove something like a Church-Rosser theorem, because it's only ever going to go one way. And we don't have to worry about how to implement it. We don't have to make those decisions about call by name versus call by value. So you won't often see a Turing machine presented in this form. This notation is much more popular with the lambda calculus type logicians. When you read Turing's paper, you really get the feeling he was working by himself, and he wasn't hugely aware of what everyone else was doing. He's inventing a lot of his own notation to do this, which would have all been a lot easier if he'd have read a little bit more of other people's work. In fact, there's a great point somewhere in the paper where he thanks one of his friends for help with references. It's the kind of thing you'd only write this if you've finished your whole paper. You've done your maths, you've written it up, and then you go and ask your friend to help you find some other things to cite that might be similar to what you've just done. So if Turing had been more familiar with this approach, we might have seen it all presented more in this style in the first place. But by putting it into this style, it makes it easier to compare with the other logics we're looking at. And in particular, we see this determinism is very prominent. Okay, when we bust out into workshops, I think I'm going to ask those of you who are interested in this to try running some little Turing machine programs. Well, technically to try running some little Turing machines, right? One Turing machine is one program. Now, this is the FSM in a particular Turing machine which executes a particular program. So this example, I'll just introduce it. I'll let you guys go through the detail. This is a doubling program. So the idea here is you're going to start with a tape. We can easily represent natural numbers using a tally notation. Okay, so let's start with a tape that is all zeros except for 1, 2, 3, 4, 5 instances of the digit 1. So a typical convention is to use that tally notation to represent the numbers. That is representing the number 5. Okay. So you'll see other Turing machine programs which have multiple inputs. So for example, you can represent the number 3 there, put a 0 after it, and let's represent the number 4 there, and zeros everywhere else. So this is a program with 2 inputs. It's got a 3 and a 4. And you can keep going to make as many inputs as you like. That's not part of the definition of the Turing machine. That's just a convention that everybody uses when they design these programs. So this is a doubling program. It's going to take any natural number written on a tape and it's going to double it. So the output of that will be 10. It will be 10 instances of the digit 1 written in a row along the tape. Starting here, but here's state 1 to start. Same notation we've seen before. You might find this notation useful when you're working these out with a pencil. This notation, it shows the state of the tape and it shows the position of the head as a subscript to one of the digits. So this is the state, okay? This subscript says we're in state 1 and it shows that the head is pointing at that digit 1. In this state, now we're in state number 2 and the position of the head is here. The position of the head is on this 0. Okay? You know, ideally you'd notate it something like this. You'd write the tape out like that and you'd write number 5 right under the number to show the head is here pointing at that 1 and we're in state 5. It's hard to do that in most notation programs, so we just shift that subscript along a bit and we make it a subscript of the digit that represents the location on the tape. Okay, so this gives us a nice concise notation. This is a state of the tape at time 1. This is the state of the tape at the next time. So what's happened? What have we done to go from the first state to the second state?
We have read a 1 and shifted left.
Yep, that's right. So look, we're now here. Yeah, we've shifted left. We've not written anything. We read the 1 and we shifted left. Oh, and we've gone to a new state. Look, we're now in state 2. Yeah, we were in state 1 and now we're in state 2. So we were there in the FSM. We read the 1 and now we're here. Okay. So if you chug through all of that, you should end up with, in this case, 10 digit 1s in a row on the tape, and that is your output. Okay, here's a more complex program. These examples are from the Ulof's book, by the way, which I hope everyone has been reading, because it was the reading for this week. I just pasted straight out of the book. This is a more complex program for doing multiplication. So again, we have a finite state machine. We start in state number 1. At each time we're saying, what are we reading? What are we doing? Are we going left or right? Are we writing a 1 or a 0? I think some books use the letter B for 0. I think the idea is blank. The square can either be blank or it can have a 1 written on it. They're the same thing. And what you'll see here is an example of a subroutine. The nature of multiplication is to go around doing something again and again. Yeah, you're going to do addition many times. So you'll see a structure like this where you're calling into a subroutine called the leapfrog routine. So if you need help understanding this, go and look in the reading that I put on Blackboard in the Turing machine chapter 3. So, you know, again, you can start your tape in a configuration like this. So to represent 3 times 2, we'll do 3, put a gap, we'll do 2 zeros, everything else. And we're going to end up in a state like this with 6 1s in a row representing the number 6. Okay, well, there's the input state, 3 and 2. So again, if you want to do this as the breakout, this is a nice way to understand how the thing works. Nearly time for a cup of tea, I think. Just before we go for tea, actually programming Turing machines, you can probably tell, is going to be quite painful, right? They're so low level. So one of the first programs that anyone wants to write is a kind of virtual machine that gives you a higher level interface to the Turing machine. So this virtual machine, and this was, I think, done after Turing. This isn't Turing's work. This was someone messing with that later on. Sometimes called a register machine or an abacus machine. They're the same thing. So let's consider a different model of computation. Ooh, and if you ever got an exam question that said, talk about different models of computation, this would now be a third one to add to Lambda calculus and Turing machines, right? A register machine is a slightly higher level model of computation. So in a register machine, let's assume you have an unlimited number of registers. These are registers like you get in your CPU, okay? So register number I, and I can usually be any positive integer, including 0. So these are like memory locations in a regular PC. They're addresses. And let's assume each register can store a arbitrary positive integer again. Okay, so think of it as a bunch of pigeonholes for putting mail in, or think of it as actual memory in an actual PC. And each of those addresses can store a positive integer. Okay. And then we're going to have a slightly more complex finite state machine. And the states of this machine are different from the Turing machine. These states correspond to lines of a computer program, so we're going to call them L instead of Q. And initially you start at state 0 or line 0. And the state transitions are going to be done, you can kind of take your pick exactly how you set this up. This is one that I've chosen. This is a state transition that says, if I'm in state L, otherwise known as line number L, I'm going to say, what is the content of a particular register, the ith register. I'm going to say, if the content of this register is this number, then go and do something, and otherwise go and do something else. And the things I'm going to do are like higher level versions of the Turing machine. Okay, the things I'm going to do is I'm going to increment or decrement the content of a register, and I'm going to jump to a different state, or equivalently to a different line of the program. So this is something that looks almost like an assembly language instruction. Okay, I think you can build your whole machine just out of this instruction. I was trying to find an example where you only need one type of command, because that makes it really easy. So does that machine make sense to everyone? It's like a really simple assembly language programming model. You've got unlimited locations. Every location stores a positive integer, and you've got one command that says, look at the content of an address and either do something or do something else with a jump.
That's cool. But the name, so I understand the calling of a register machine, but as an abacus machine, is that actually a kind of computation that people do on abacus machines? Because you can see the different, what would you call them, rows on an abacus are like registers. So is there something that can be directly applied to?
Yeah, so roughly an abacus is a bunch of registers, and each register is holding an actual number. I think that's the metaphor. I don't think anyone would actually run these type of instructions directly on an abacus, but you could if you wanted to, right? Yeah, Abaci can do anything if you have the right program to run on them. So yeah, there's other ways of. Sorry.
Yeah. I wonder if that'd be easier or more difficult than implementing a Turing machine. I feel like if you're putting your little Lego set together, I wonder if this would be preferred to going to a Turing machine and then putting together a higher level program as the FSM on the head of that.
And this is almost like some of the machines that student projects have emulated. We've done so not your C natural, because in C natural you're compiling into another language, But for example, Alice, who you know, Matthew, Alice's group did a project where they created a very simple programming language, and it was based on this idea that you have 26 variables called A to Z, and they only ever store natural numbers. You know, it's almost like that kind of machine. Well, you know, we've had student projects that have simulated CPUs. So David Churchill did a project 2 years ago, I think. They simulated part of a ARM CPU, and again, they're simulating those registers. You know, you basically just have a big array holding a bunch of natural numbers, and you're pretending each of those elements in the array is a physical register. So yeah, it's possibly easier to simulate this than to simulate a Turing machine, or maybe about the same.
Okay.
But both easy to do. Okay, but the interesting thing to do, and you know, again, this is not directly accessible, but it's a great exercise to do. You know, can you write a Turing machine program as an FSM which simulates the register machine? That's what the idea is really for. And it shows you how to do it in the book chapter that I put on Blackboard. Not going to go through the details, but roughly you're going to use this convention again. You know, here is the tape of the Turing machine, and we're going to use blocks of ones to represent the states of each register. Right, so here's the state of register 2, here's the state of register 3, here's the state of register 4. The other registers are empty. And you can kind of tell already this is going to get very, very messy, right? What's going to happen if you want to add 1 to register 3?
Well, you need to have a bigger register. Isn't it easier to have registers as discrete but fixed sizes, and then you can combine registers if you want larger numbers? This feels like a more complicated way of going about it.
Yeah, so again, you know, for theoretical purposes, we'd like each register to hold arbitrary natural numbers, which is actually more powerful than what a practical
that makes sense.
can do. Yeah, okay. If you said each register is only going to be 64-bit, this will be a lot easier to do. But when we do meta logic, our life is going to be easier if everything can go to infinity, because then we don't have to worry about what happens when you hit the top limit of the register.
And you said that it was going to get messier, but it's really getting messier at the Turing machine level if we're implementing this on a tape, not at the level of the register machine itself, because the logic behind expanding and contracting those is dealt with in the finite state machine.
We're gonna shift all the mess down to the lower level system, right? So you know, let's take a worse example. Actually, what happens if you want to add 1 to register 2 then? Yeah, this is going to have to expand, isn't it? We're going to have to put a 1 here. But then what happens to the rest of the tape?
Yeah, now you have to push everything. You have to copy
everything. You're going to have to go, I mean, it's not that hard, actually. You just need a little subroutine. And remember, we're not treating this as a practical computer design.
Yeah. That got me. Because, like you said, it's not hard. But then if I was writing a program and I was using this kind of paradigm for dealing with data, I would start twitching.
I mean,
I see what you mean.
This is exactly what my compiler's group project just ran into when they've been doing arrays and they represent their data in the array, and they say, what are we going to do when the user wants to make the array 1 element longer? And that's called a vector in most languages. You know, they're like, ooh, that's going to be really hard, isn't it? We're going to have to totally reshuffle all the memory around to make a vector. And I'm like, yep, that's why vectors are slow. And we learned some. But yeah, from a theoretical point of view, we don't care how long any of this takes, as long as it halts eventually. So it's in the program, it's not very hard to write a little program that just says take everything on the tape and shift it along 1 space to the right. So if you want to add 7 to register 2, you know, go call that routine 7 times. That's easy to do. Shift everything to the right. Do it again, and then fill in a bunch of 1s in here. Similarly, if you're going to decrement, you're going to have to shift everything 1 space to the left. But in theory, it's very simple. It would be very slow to run on a real machine, but nobody cares because this isn't a design for a real machine.
Yeah.
So, again, if you guys want to play around with this, it's in the book. You can construct a big Turing machine FSM out of a bunch of subroutines, and the effect of that, along with this convention for encoding the tape, is to emulate the register machine. And we're going to come back to this hopefully later in the module, because when we want to do fancier things with Turing machines, it's a lot easier to think in terms of register machines than to have to faff around fast forwarding and rewinding tapes all the time. So in particular, the register machine is a real RAM. It's a random access memory. That means you can read and write to any register in a single instruction, whereas the Turing machine is not a RAM because it takes you longer to fast forward and rewind to distant locations than to nearby locations. So yeah, at this level, you now have something that looks very like a simple CPU or a Babbage architecture. You've got a bunch of addresses, read and write things, a bunch of commands that look like assembly language, and all set up with jumps. You think of the states as lines, and now you're on familiar ground. This is the equivalent of what we did with Lambda calculus when we turned it into something that looks a bit like Haskell. Yeah, if you start with Lambda calculus, you end up with Haskell. If you start with Turing machines, you end up with assembler, and then you end up with C. So, depending on your point of view, if someone was to set an exam question which said, what is the best model of computation, depending on your point of view, if you like Haskell, it's going to be Lambda calculus. If you like assembler and C, it's going to be Turing machine. Shall we go and have a cup of tea?
Sounds good.
Yeah. Let's take 10 minutes.
Everyone make sure that you don't forget to do the attendance code for the workshop as well, because that is an hour and not 2 hours after the thing. I keep on messing this up.
They're in the text chat. Right, we'll take 10 minutes. Let's come back at 3:25, and then we'll talk about the meta logic for Turing machines, and then we'll go and do workshop stuff after that. Okay, see you at 3:25.
Good.
Elliot, if you're there, the workshop code is 216252. For some reason I can't post in chat. So yeah. So in case you missed that, 216252.
Hello.
Oh, welcome back.
Just reading through the paper as well. Now that you've said that he was someone who kind of just went in and did stuff, didn't have too much reading about the place. I'm seeing it everywhere throughout the paper. You've coloured my mind. I've been primed. There's a sentence here that says, if a computing machine never writes down more than a finite number of symbols, it will be called circular. That's a triple negative, basically. I'm a little bit upset with that.
So, yeah, let's just have a little look over this. Yeah, let's see how much pops out right away. You know, the first thing about Turing's paper. Well, look, here's the date. Okay, so these dates are important because you have to compare them with Church, and the paper is published after the Lambda calculus paper. Okay, so it's still 1936. You know, the first thing you notice then is the title, right? The title of the paper is Uncomputable Numbers. And what's the linguistic term for this? The object of this phrase isn't the computer, it is the numbers, right? The numbers is a noun, and computable is a adjective.
Adjective.
This paper is not about computers. This paper is about numbers of a particular form, and this paper is actually brilliant. This paper is actually genius and one of the greatest papers ever written by anyone, but it is not for the reason of inventing computers. It is for the reason of understanding these numbers. So mathematicians have this bizarre way of defining the real numbers that is very difficult to understand and to do anything with, and in particular is completely unusable in computers. So we just don't use it. What Turing actually does in this paper is he redefines the real numbers. He defines his own set of numbers, which have all of the useful properties of the mathematician's real numbers, but without all of the difficulties of them. So he defines a different set of numbers called the computable reals. Well, I always think we should call them the Turing reals. I think we should give them a letter T for Turing, you know, like we do with the letter N for natural numbers and so on. So I use this in some of the stuff that I write. Never really caught on yet, but this is an absolutely amazing study of what the real numbers are, or what they should be, how they should be defined. And this is a definition that in computer science we can actually use. You can actually represent Turing reals in computers and to some extent do calculations with them, and they avoid a lot of the problems of the mathematicians' real numbers. So now let's take a look at the first sentence, right? The computable numbers may be described briefly as the real numbers whose expressions as a decimal are calculable by finite means. So these are the mathematician's real numbers, and he's going to define computable numbers as a subset of the mathematician real numbers, which are calculable by finite means, i.e. the ones we can actually do anything with on a computing device. And we're going to chuck out all the rest of them. So this question, hand from Matthew?
This just popped in mind. Is that then the same kind of distinction then? Because what he's saying is, let's say the computable numbers, there's a set of computable numbers, and we'll call those true. It's true that they are computable, but then he's saying that there's a subset of the things that are true, which are also provable. And if you say it like that, is he basically defining things in the same way that Gödel would have defined the separation between things that are provable and things that are true?
It's a very similar idea, yeah. So look, the next thing we notice on this page is he's talking about Gödel, right down here, right? He says, look, conclusions are reached which are superficially similar to those of Gödel. So yeah, he's certainly thinking in those terms. So yeah, a number that is uncomputable is playing a similar role to a logical statement that is unprovable in a Gödel star setup. And yeah, Turing's definitely reading Gödel from 5 years before and applying that same idea to numbers. Yeah, Gödel's theorem is about logic. Turing's paper is about numbers, but he's going to do the same thing to number that Gödel just did for logic. Okay, so look at the next part of the title. This unpronounceable German problem roughly means decision problem, and this is the same problem that Gödel is working on. You know, are there things that have no algorithmic solution? And yeah, for Gödel, he found the first example of it. Gödel found the first unprovable thing, and now people are starting to find more examples of statements that are unprovable. So you can see that people still write papers with this kind of title, all right? Nowadays we probably have a colon instead of a comma, but the real title of the paper is on computable numbers, and then as an afterthought, we're going to say, oh, and there's also an application to the decision problem. You know, once we've done our main thing, we're going to chuck in an extra section, and we're going to get a new proof of Gödel's idea popping out as a byproduct of the main thing we were doing, which was defining computable numbers. Okay, so look, let's go to page 2, and let's take a look at this paragraph. Right, this introduction has obviously been written after the rest of the paper. You know, as computer scientists do today, they do the real work, and then normally the supervisor writes the introduction and the student writes the real work section. But there's this little afterthought here. He's written this right at the end, and probably this has been inserted after the paper was reviewed, and almost certainly the paper would have been reviewed by Church. And as reviewers do today, the main function of a modern reviewer is to encourage the author to cite their own work. You know, you always read it and say, this is a great paper, but it would be much better if you put in 7 references to Fox 2016, 2015, whatever, which is super relevant to the work you're doing. So almost certainly this would have been reviewed by Church, and Church has told him he has to put this in. So you know, here he said, in a recent paper, Church has just done exactly the same thing that I'm going to do. He's just introduced the idea of effective calculability, which is exactly the same as my computability, differently defined. Church also reaches similar conclusions about the decision problem to what I'm about to do. Church has just done that too. And to demonstrate that my model and Church's model are equivalent, I will demonstrate that in the appendix. And if you look in the appendix, you'll see someone's made him put in a load of lambda calculus and demonstrate that his model is exactly equivalent to what Church has done. So yeah, let's have a little tour through this paper. You know, this paper and the Lambda paper are such foundational documents. You know, it's like the American Constitution. So everyone should at least look at them once in their career. So you know, he's going to do this using that model of computation. He's going to define that machine that we now call the Turing machine for the purpose of showing all this stuff about computable numbers and the decision problem. And he's going to set up that machine to be as mathematically simple as possible so that it's easier to do the meta logic on it. So you know, this is all the stuff we've just been talking about. We're talking about the states of the machine. There's those queues, the symbols of the machine, scanning the symbol, right? And again, all this stuff is taken from the paper tape machines of the time, but he's trying to set up the simplest version of it so that you can do the meta logic. The machine is supplied with a blank tape set in motion, starting from a state. The sequence of symbols printed by it will be called the sequence computed by the machine. That's the output, is the final state of the tape. There's no diagrams in here, possibly because they were hard to print in those times. But we should just about recognize this type of notation. If we just take a bit of a flick through, here's the left and the right moves. You'll see these are the different state names. I think in this case he's using letters instead of our numbers. Here's a set of configurations of the tape. This is like the thing we just wrote down, where we're showing what's on the tape and where are we and what state are we in. That's the origin of this writing the state number underneath the tape up above. And you'll get a notation similar to these tuples that we've seen, the reduced notation, where you just put the state and the symbol and the action in a bunch of brackets. And that notation is nicer for doing the meta logic about. So, you know, after that, it's all about this notion of number. I'm going to talk in a little bit about these ideas, how to enumerate sequences and pair things with natural numbers. This is now going into the meta logic. This is neat. This is a example of a Turing machine that simulates other Turing machines. So, you know, as we saw, you can simulate a register machine on a Turing machine. You can build a Turing machine that simulates arbitrary Turing machine. And this is possibly the first example of a virtual machine showing up anywhere. In architecture, we talked about this idea appearing very naturally in a whole bunch of projects, and it wasn't considered exciting at the time. This argument about who invented the first electronic computer often comes down to whether the ENIAC was a real computer or not, because there was a version of it that had a virtual machine, and that VM was just implemented by the programmers who got bored of having to flick switches all the time, and so they just wrote a little program that read in the state of the switches as data and turned it into a von Neumann architecture. So, you know, that's called a universal Turing machine, when you simulate a Turing machine on another machine. This is something called a diagonal process that we're about to talk about. So this is all to do with understanding what's computable and what is uncomputable. It's to do with different types of infinities that was in common use in the mathematics of the time. Yeah, and now we get to the numbers. This is the point of the paper. Here we are defining the computable numbers. We're defining the subset of the real numbers that are computable and are therefore useful. And you know, really, this should have blown away the mathematicians' definitions of the reals, which has always been very weird and not very useful. You know, it's an interesting bit of sociology why the rest of the world didn't pick up on this as much as they could have done. Yeah, large classes of numbers which are computable, giving lots of examples. And let's just skip forward and take a look at that appendix. Well, there's the section on the decision problem, right? That's going to drop out towards the end as a byproduct of everything else he's doing. You know, here's a new proof of a Gödel style result. Yeah, so here's the appendix. Yeah, this is going to be linking the work to Church. So now we're talking about lambda calculus. Yeah, Church has just done all this. Very obviously, this has been added in after the rest of the paper. And it's saying, yeah, okay, Church already did this all a few months ago. And here's an explanation of why the two models are completely equivalent to one another. So absolutely amazing paper for the reasons of understanding numbers, not for defining computation or for inventing the computer, which had all been done before. But still absolutely genius. You know, real Einstein level genius of understanding numbers. Okay, let's try and make some sense of the meta logic then. So we've mentioned a few of these concepts like diagonalization, looking at Turing's paper. So to understand what's going on here, we have to go and look at a little bit of pure mathematics. So I always try to be very clear that logic is not mathematics. It is a separate subject. It is prior to mathematics. Mathematics can build on it, and so can computer science, and so can a whole bunch of other disciplines. But when we're doing logic, we're doing logic. We're not doing mathematics. This is a case where we're going to look at some ideas which really are about numbers, specifically mathematical ideas about numbers. So this is a case of taking an idea from mathematics now and applying it to logic. You know, as many subjects do. You can take ideas from mathematics and apply them to physics or geography or anything. But this is a relatively rare application of mathematics coming down a level into logic. And this idea is to do with sizes of infinity and the different types of infinity that can be shown to exist. So before we go to infinity, let's consider finite sets because they're easier. Okay, we will introduce this notation to mean the size of a set. So S could be a set. For example, here is a set containing James, John, and Mary. Well, this one's called A. Okay, that's a very simple set. It consists of 3 human beings. What is the size of this set? What is the size of A?
3.
3. Easy. Yeah. Good. And we know what 3 is because we defined it really well last week. Yeah. Okay. Good. So the size of set A is 3. Okay. Here is another set, B. This set contains cat, dog, and tiger. What is the size of B? Okay. The size of B is also 3 because the set has 3 elements. Yeah. Let's define what it means for 2 sets to have the same size. Okay. Let's define 2 sets as having the same size if you can find a way to pair up their elements 1 to 1. Okay. So let's take set A and set B. And the point is we're going to do this without having to discuss what their size actually is. We're going to try and say they have the same size, but without mentioning the number of their size, which is a weird thing to do, but it will turn out to be useful later on. So for example, you could make a mapping that makes cat go to James and dog to John and tiger to Mary, and you've demonstrated that for every element of this set there is an element of that set and vice versa. Now here's another way of doing it. You could pair James with dog, Mary with cat, and John with tiger. And if you can find a way to do that, you have shown that the 2 sets have the same size. Happy? Okay. Right, now let's make it a bit harder. Now let's look at some unlimited sets, which just keep going. We are going to keep the same definition. We're going to say that 2 sets have the same size if you can pair up their elements. But now we're going to look at sets that don't have an end. They are infinite because they keep going. So for example, the set of natural numbers. Okay, the natural numbers goes 1, 2, 3, 4, ... and it just keeps on going. So it's possible that there are other sets which are the same size as the natural numbers. And we give this meaning by saying this occurs when you can find a one-to-one mapping between natural numbers and things from your other set. So let's give a name to the size of the natural numbers. So the size of set A was 3. This is a new thing that we haven't seen before, so we're just going to make up a symbol and a name, and we're going to call it this thing, which is pronounced L0, I think. It's the Hebrew letter A, as in alphabet. Alf0 from the alphabet. And the fact it has a 0 in it suggests there might be more of these things coming along later on. So we say this is the size of the natural numbers. It is L0. So any set that you can pair up with natural numbers is also going to have size L0. And this can be a bit counterintuitive, right? For example, the size of the set of even numbers is the same as the set of natural numbers. Okay? Now you might think there are only half as many even numbers as natural numbers, but in fact both of them are infinite and they both have size of 0. And you can demonstrate that, for example, by doing this. Here's a pairing which maps natural numbers to even numbers. So the first element of each pair is a natural number, 1, 2, 3, 4. So we've got all of them. And we're going to pair them up with 2, 4, 6, 8, and so on. And so we have discovered a simple one-to-one mapping between the naturals and the evens. So they're both infinite, but we say they both have the same size because we can make that pairing. So does that sound crazy?
Well, when do you start dealing with something like that? I don't know. I think the terminology saying that they have the same size is a bit weird, but saying they're on the same order of size, makes a lot of sense to me.
Sometimes they use a new word. They call it cardinality.
Yeah.
To get away from any intuition you might have about the meaning of the word size. The cardinality is just defined as this pairing process. You can take the natural numbers and remove the first 10 numbers, right? Remove all the numbers from 1 to 10. And you can show that the numbers that are left have the same size as the whole set of natural numbers, because you could pair them as, 1 goes with 11, 2 goes with 12, 3 goes with 13, and so on. And you can still find a one-to-one pairing. So you can do it with primes as well. Again, we've got here are the natural numbers, and here are all the primes, and we've managed to find a pairing up of natural numbers with primes. So the set of naturals has the same cardinality as the set of primes. Less obvious is fractions. So a fraction is two natural numbers, such as 3 and 4, and one's written on the top and one is written on the bottom. And you might think there are more of these than naturals because each fraction has 2 components that is a natural. But you can in fact find a way to order the fractions, which goes like this. So think of a square. Let's do 1 over 1, and then you can do 1 over 2, and then you do 2 over 1, 2 over 2, then 1 over 3, 3 over 1, then we do 3 over 2. Let's do all of the 3's. We've got 2 over 3, 3 over 3. Now you notice I'm writing these down in an order. Okay, the fact that I'm actually writing these on the slide one at a time is important, because the order that I'm writing them is the order that we're going to pair them up with the natural numbers. Okay, 3/4, 4/3, 4/4. So I think the order I wrote them was something like that. Okay, you can easily find an ordering. So let's say this is going to go with 1, this goes with 2, this goes with 3, this goes with 4, 5, 6, 7, 8, 9, and so on. So pairing things with the natural numbers is equivalent to being able to find a sequence that you can write them down in, which you can do with fractions. So Maybe even less obvious is the set of programs. So this is going to be relevant. Can you find a mapping from programs to numbers and vice versa? And again, you can, because we've seen that there are ways to turn a program into a number. So not every number is a program. For example, ASCII encoding. If you just take a huge random number and represent it as an ASCII base 256 coding, most of those you'll write down the sequence of characters that the number represents, and they'll just be complete garbage, and they're not actually programmed. But some of them
that
are.
Depends on the interpreter, right? If I define an interpreter which takes all of any sequence and takes the lowest bit and uses that in order to create a new program, or any arbitrary other way of interpreting that sequence, you could say that technically all programs are all digits could be considered programs.
Okay, good. Yeah, so you might find an encoding where everything at least looks like a program. Good. Doesn't actually matter for this argument, because whatever programs you have, you can just put them in an order, because you can always tell if one program is a higher or lower number than another program. And again, we'll argue about that maybe later on. But assuming you could do that, at least, you could then put all your programs in an order, pair each one with a natural number, and you've got the same cardinality of natural numbers as you have for programs. So yeah, for anyone who's not seen this before, here's a way of coding a program as a number using ASCII base 256. So here's a very simple program, print hello. We're going to take each character of this, and we're going to read it as a big number in base 256. So that closing bracket is here, and that takes the value of 1 because it's in base 256. So this column of the number is how many 256 to the zeros you have. So it's not going to take the value of 1, it's going to take the value of whatever the ASCII code for a closing bracket is. It's the ASCII code times the number 1. This takes the number 1. Now, this number here, Gary?
Charles, just on the fractions element, these fractions obviously will go to 1, and this is paradox thing where you never felt it reached, and all that sort of stuff. What happens when you get 1.5? What's the?
Oh, so yeah, those numbers are included, right?
Yeah.
This sequence doesn't converge to anything. You remember when I wrote them down? I had this way I'm going half, a third, a quarter, but this way I'm going 2/1, 3/1. So these fractions have already gone above 1. Okay, 2/2 is equal to 1. That's actually a repetition of a number we've seen already, but we don't care.
Okay. Yeah.
So you've got 2/3 there, and you've got 3/2 there. So there's your 1.5.
Okay, sorry. Yeah, very obvious
and
now.
then, and then when we come to order them, we're going to do something like this. There's your ordering, and that gives me a way to stick them into that sequence. Okay, good. Anyone know the ASCII code for closing bracket? Is anyone that much of a geek? All right, it has some number between 0 and 255 inclusive. Similarly, the letter P has a number. Say it's 37. I don't know. This is in the 13th column of that number, so it gets multiplied by 256 to the 13th. So you can view this program simply as a number written out in base 256. In hex, you have 0 to 9 and letters A to F. In ASCII, you have all 256 different characters representing digits between 0 and 255 inclusive. Okay, so it turns out that ALF0 isn't the only kind of infinity that is out there. There are infinities that are bigger than ALF0 in the sense that there are too many elements to be able to pair them up with the natural numbers. So, for example, consider the set of all possible functions from natural numbers to Booleans, okay? Every possible function that takes a natural number as its input and gives you 0 or 1 as its output. So this was done by Cantor in 1891, okay? Sometime before the computational logicians. First of all, consider a function f. That's just one possible function from naturals to Booleans. And let's write down all of its possible outputs, okay? So this is a function. It takes a natural number as an input, and it gives you a Boolean as its output. And if you give it the number 0, it gives you this. If you give it number 1, it gives you this. If you give it 2, it gives you this. If you give it 3, it gives you this. So, for example, this function might give a particular set of binary numbers. Okay, so this is enumerating all the possible outputs of that function, and that's really defining what f is. It's telling you what this function is. What we're going to do now is prove that there are more functions than there are natural numbers. Okay, in the sense of this definition of size. And the way we are going to try to do this is we are going to make a list of all the functions. So f0 is one particular function. And remember, every function takes a natural number as its argument and gives you a Boolean. So here are all the possible values that this function is going to take. We're completely defining what the function is as a function of all these different natural numbers as the input. And this is going to be a bunch of binary digits like this. Now take the next function. Take function number 1. And we're going to write down, again, these could be anything. These are all the different outputs that function gives you. Now take function number 2. Do the same thing. Now all of this is done assuming that there are the same number of functions as there are natural numbers. Okay, we're going to suppose, this bracket and suppose means let's make an assumption for a while and see what happens. So suppose we have a method that actually does pair each function with an integer, so a natural number. Okay, if that assumption is true, then we can write all our functions in a big list like this. Here's the 0th function, here's the first one, here's the second one. And each of those functions has a definition of what are all its outputs for different natural numbers. Does that make sense?
Yeah, but now I'm a little bit confused, because surely we can encode any function as a program, but we know that the program have the same, the set of programs has the same cardinality of the set of natural numbers. So
yeah, that's a very good line of reasoning. Yeah, we would, if we were able to compute every function, that's something you're assuming, right? If every function was in fact computable, then we could go to number it, and then we could use the stack of programs in place of the stack of functions. Yeah? That would be the case if every function was in fact computable.
I see. Thank you. Okay, that makes sense.
Yeah, at this point we're just talking about every possible mapping from the naturals to the Booleans. Okay, so you're gonna end up creating this large matrix, infinitely large matrix of zeros and ones, and each row represents one of the different functions that you know about, and each column tells you what that function does when you give it a different input. Okay, and the whole thing is full of zeros and ones. Right, what Cantor is going to do now is derive a contradiction from this. He's going to show that this supposition we made leads to badness down here. And whenever you have this pattern, when you make a supposition and get a contradiction, you close your assumption and you say, therefore, the supposition must have been wrong. And that's how the proof is going to work. Okay, so let's go back to this matrix full of binary digits then. I think Cantor actually did this with decimals, but we're computer scientists, so we're going to be binary about everything, apart from gender, which has to be non-binary. Yeah. So what we're going to do is create a new function that wasn't in the original list. Okay? Our supposition was that we have a method that pairs every possible function with a natural number. Yeah? Because of that supposition, that means every possible function is now somewhere in this list. Every possible function exists as a row somewhere in the list. And now we're going to show that there is in fact another function that we have missed. Okay, whatever functions you put in the list, we're going to use to create a new one that wasn't in the list. Has anyone seen this before? Anyone know how to do this? No? Okay, so this is called the diagonal argument, or Cantor's diagonalization argument. We're going to create a function like this. We're going to take the diagonal of this matrix. We're going to read off the number in the diagonal, which in this case is 1, 1, 0, 1. Okay, there's a 1, 0, 1. And then we're going to invert all the bits. So we're going to invert it, so we get 0, 0, 1, 0. Okay? And this goes on forever. It's an infinite list. And so therefore this goes on forever as well. Now the question is, this now describes a function. The result of doing that has created a new function. The question is, does this function already appear in the list? Or is it different from every function in the list? So first of all, let's compare it with the first row, okay? Is our function the same or is it different as the first row? The first row says 1, 0, 0, 1. And we've got...
That is quite different from the first.
Yeah, okay, it's completely different. So I'm going to give you a really simple proof of why it's different. I'm not even going to look at all the different digits. I'm only going to look at the first one. Look at the first digit, right? The first digit was 1. And the first digit here is 0. So they're different, right? Okay, take the second function. Is our number the same as the second function? And again, let's make it easy. Let's say only look at the second digit. Is it the same or is it different?
Different.
It is different, and it's different precisely because we flipped it to make it different. So our new function is not the same as row 2. Now let's look at row 3. Okay, is our new function's third digit the same or is it different as row 3?
Yeah, again, by definition, we've said that across the diagonal, it is never going to be the same digit. That's the line horizontally.
Okay, so look, we started by assuming that we got this method to pair every function with a natural number, okay? Making that assumption, we then created a list of every possible function. Because this is row 3, the natural number is 3, and so you get the third function from that pairing sitting down there. So based on that assumption, we said we now have all the functions, we're putting them all in the list, and now we've given an algorithm for creating a new function by doing this and inverting the digits. And this function is different from all the functions in the list. Therefore, we did not actually have a list of every possible function in the first place. If you give me any list of functions, I can always do this. No matter what functions you give me, I'll write them down, I'll do this diagonalization trick, and I'll create a new function from all the ones that you gave me in the first place. So therefore, our assumption must have been wrong. We cannot, in fact, pair each function with a natural number. And that means, under this definition of cardinality, it means there are more of these functions than there are natural numbers. So the set of functions then has a larger size, or a larger cardinality. And this was controversial for a while, and the resolution is complicated. It was proposed that we should call this cardinality alpha1 to show that it's the next biggest kind of infinity after alpha 0. And for a very long time in the 20th century, there was this question of, can you find a number that is bigger than alpha 1 and small, bigger than alpha 0, but smaller than this purported alpha 1? And the answer to that question is very complicated indeed. So I'm not even going to go into it here. But the point is that the cardinality of these functions is bigger than the cardinality of the natural number. Now, what does this actually mean, right? As Matthew just pointed out, the natural numbers have the same size as the set of programs, all possible programs. But we can see here then there are functions which cannot be paired up with a program. So there are functions that are possible that cannot be expressed by any finite length halting computer program. And there are a lot of them. Actually, most functions are uncomputable because the size of this set is massively bigger than the size of the natural number. So this is Turing's insight. Okay, he's taken this old trick from 1891. And so Cantor didn't do this on programs. Cantor was doing it on functions. He's just saying there are more functions than there are natural numbers. But Turing's going to take that as his cue for uncomputability, for saying there are functions that cannot be computed by an algorithm, as Church had done several months earlier. This is a proof that some of these functions exist. It doesn't tell you what they are. It just tells you that they're out there somewhere. And there's this much larger infinity of things that computers cannot do than the set of things that they can do. Here's the argument then. The set of programs has size alpha 0. The set of functions, so that should be B for Boolean. That's a typo. The size of that set of functions is bigger than alpha 0. Therefore, most functions are uncomputable. So Turing is now going to take that as his cue to go looking for a particular function which is uncomputable. And he's going to come up with basically the same thing that Church had come up with. It's going to be studying the halting problem. It's the problem of being given a program and determining whether or not it ever halts. Now with Lambda calculus, we saw that you can construct these programs that never halt out of things that look like the Y Combinator. They just go on reproducing themselves forever. With a Turing machine, it's actually much easier to make a non-halting Turing machine because you just have a loop. You just say stay in the same state forever. It's absolutely trivial. Just make state Q1 and say whatever the symbol is, go around. Yeah, whether you're in symbol 0 or 1, you just stay in the same state. So Turing's going to make basically the same argument as Church now. Some functions are uncomputable. Now let's go looking for a specific one. So here's our task. This is the halting problem, and we're saying, given a Turing machine and a particular input, decide whether or not it will halt. So remember, a Turing machine is defined by that finite state machine. The input is defined by what's on the tape at the start. And we've already discussed how you can encode all these things as natural numbers. You can take the whole Turing machine and encode it as a single big integer. Yeah, so you could write down the Turing machine in whatever representation you like in an ASCII file, and then take the integer value of that ASCII file. And the Turing does it using these 5 tuples. Yeah, he's got state 1, symbol 1, movement, symbol output, state output, whatever. You can take the list of these and just encode them all to make a massive integer. So you can encode your Turing machine as a single natural number. Let's call that M, or M of the Turing machine. That's an int representing which Turing machine you're going to use. And then we have N, which is an int representing which input you're going to use. And it doesn't really matter how you code them, right? You could do it using ASCII or coding, or at the time everyone used what is called Gödel numbering. This is a base system that uses prime numbers rather than powers of 256. I like to do everything in base 256 because it's much easier to compare with things we know about, like ASCII. But yeah, in the 1930s, everyone liked using Gödel numbering instead. Okay, and now we're just going to make the same argument that Church had just made. Suppose we have a Turing machine called H, which is able to solve the halting problem. So H is going to take a pair, Mn, as its input. Okay, so remember, M represents a Turing machine, N represents an input on the tape. And here's our Turing machine tape. We're going to encode the number M by a load of 1s on the tape. We'll put a big 0 in the middle, and then we'll encode the number N by some 1s on the tape. Okay? So this is the halting problem Turing machine. This is our magical Turing machine called H. And it is defined as taking this as an input. It takes a description of another Turing machine and a description of a input for that Turing machine. And it is supposed to tell us whether or not M is going to halt when you feed it with N. Right. And if the thing halts, it's going to output a 1, and otherwise it's going to output a 0. So let's say the state of the whole tape will be covered in zeros, and if the thing halts, you get a 1 there, and if it doesn't halt, you get a 0 there. The whole tape is full of zeros. All right? Happy with that? Now this is just what right. Yeah, just what Church did. Suppose you have a magic machine that can solve the halting problem. That machine takes 2 inputs: description of the machine, description of the tape, both encoded as ints, and it outputs a Boolean. Right? Okay, so now what we're going to do is blow it up. So anyone reading Gödel-5, this is like putting the record in the record player. Yeah, there's a vinyl record player, and every mechanical device has a frequency which makes the machine itself vibrate and fall apart. And so you're going to go and make a special record that just contains a massive loud sound at the frequency of the machine to blow the thing up. That's what we're doing here. We're going to blow up this Turing machine H. All right, and here's how we're going to do it then. So we suppose that we've got H. We are now going to make a new Turing machine called H star, and this is going to be a relatively small modification of H. We're going to use H as a subroutine. So all H star is going to do, it's going to call H with that input, and if H is true, then loop forever. If H is not true, then halt. So you can imagine H is some giant finite state machine like this. H star is just going to be a little bit of extra logic which encapsulates H. It's going to call out to H, look at its result. If H halts, then we're going to spin forever, and otherwise we go to a state that halts. And then, just like Church did, And just like Gödel did first, we then make a strange loop. We feed the thing into itself. So now we're going to say, what will the new machine H star do if we give it H star as an input? Actually, with anything on the input table, doesn't matter. So now we've taken our magic halting machine, halting detector. We've extended it to make H star, and now we're going to feed a description of it into itself. We're going to say, do you halt when given yourself as an input? And exactly as we saw with Church, the logic of this, well, you can read the logic directly, right? H star says, if H star halts, then loop forever. And if H star loops forever, then halt. So it contradicts its own definition. If H star halts, then it doesn't. And if it doesn't, then it does. Just as with Church's proof, this is a contradiction. And therefore, when you get a contradiction, you then go back and you say the thing that we suppose is incorrect. Therefore, we have disproved the thing that we assumed. So no such Turing machine can exist. So this is Turing's solution to the halting problem. But you have to understand the reason he's doing it is to give an example of one of these uncomputable functions. Right? He's gone through this diagonalization argument. He's said functions must exist which are different from all the functions we can make a list of. Something has to go here. And if you're reading the Boulos book, this function is called D, and the other one's called H. And he's used that to go looking for such a thing. So now he's giving a constructive solution. He's saying that this is how you actually find one of those functions. So mathematically, this function does exist. If you're God, you can look at a Turing machine and there is some objective truth about whether or not the machine actually halts or not. It is a property of the machine, whether it's going to halt. But you cannot create an algorithm, a computational algorithm that is able to actually implement that function. The function exists, but it is an uncomputable function. So no Turing machine can ever solve the halting problem. No Turing machine can ever evaluate that uncomputable function. Which is exactly what Church had just shown a few months earlier. But Turing did it from scratch using a model based on paper tape and finite state machine. So these two models of computation then, the Lambda calculus and the Turing machine, they represent these two very different strands of what we now call computer science. You can see the Turing machine is easier to understand because it is based on the actual computing machines of the time. It is based on machines like what we studied in computer architecture. It's based on the Babbage engine and all the engines that came after it, like the IBM Horror machine. So it makes it very easy to understand, but the problem is it is deterministic and it is therefore serial. You go through those rules one step at a time in a series, and your proof tree is just applying that same sequence every time in a series, a deterministic series. And we've seen how that leads to the register machine, that leads us to assembly programming, and assembly programming leads us to C, and C leads us to C++. The Lambda calculus, on the other hand, has come from the other half of what we now call computer science, which is the logical tradition itself. It's come from ultimately Aristotle and Boole and thinking about computation as a form of logic, of logical inference. The Lambda calculus is a logical calculus. We've shoehorned the Turing machine into a logical calculus, but it was actually quite hard to put it into that form. And it looks silly, just with a chain of sequence that are all deterministic. So in the Lambda calculus, you end up with what looks more like AI logic. You have a choice of which rule to apply at which time, corresponding to something that looks like call by name and call by value. And it turns out in the Church-Rosser theorem that it doesn't actually matter what order you do those evaluations. And what we are finding now in the 2020s is our serial computers cannot go any faster. You cannot go on making machines that are based on Turing machines and expect them to go faster anymore because they get too hot. And so we have to make things run in parallel now. And the Lambda calculus and the functional programming languages that we've seen can be derived from it and built on top of it. They have this property that it doesn't matter what order you do the evaluations in. You can pick different parts of a Lambda expression and evaluate them, and you can do that in any order, and in many cases you can do it in parallel. And that's absolutely critical to the kind of computing that we have to do now. We have to think much more in terms of parallel computing than we used to do. So the Turing machine leads us to C++, the Lambda calculus leads us to Lisp and Pascal and ML, and then ultimately to map-reduce algorithms and to ideas that are now being used in cloud computing. A map-reduce is a function of exactly that form, where you're going to parallelize all the pieces and then bring them back to reduce them. Much easier to do that if you've come from the Lambda tradition than from the Turing machine tradition. But with Turing, you also get a definition of computable numbers, which we'll talk about later in the module if we have time.
I have one last question before we head on to the workshop stuff.